We only needed 30 megahertz. So what we also can do is just we can kill the bandwidth. Well, we don't have to go back to 30 megahertz, but let's say that we make the bandwidth so much smaller that our second pole becomes exactly at the square root of 2 times the bandwidth. Then we have a flat frequency characteristic, which means that we are going to increase the time constant of the first pole. Then we know what to do. Then we know what to do. We can just place a capacitor in parallel with the second stage, because that will decrease the gain of the integrator. So basically, since the pole's already in the origin, you cannot bring it closer, but the integrator gain will be lower. So we are reducing the loop gain pulse product to an amount such that the second pole is exactly at the square root of 2 times the new bandwidth. Well, we know what the second pole is. This should be the square root of 2 times the new bandwidth. So we know what the new bandwidth should be. We can take the ratio of the old bandwidth and the new bandwidth and square it, because we have a second order system, and the bandwidth and the C is only affecting for the first order, CP. So then we have the design equation. So we insert the capacitor in parallel with the capacitor, and you can also, if there was an inductor but there's not, insert an inductor in series with an inductor, and the low frequency loop gain is reduced. We just, well, in this case you couldn't say we burn it, but we it is really gone in CP, in the current in CP. It is not available for the loop. So for distortion, you can already see this is not really beneficial, because we are reducing loop gain. So this is then the equation that you can derive from the loop gain pulse product, the square root of 2, and you have to square the effect, the whole thing. And then we know the value of CP, and we can simply calculate it with SlideCap, put this design equation there in SlideCap and calculate the CP and see what comes out of that. Well, let's do it. Let's go to our last option for compensation, which is the BR, stands for bandwidth reduction. And run the thing again. And now look what we are doing, by the way. Look at what we are doing. We have a parallel capacitance of 2.2 PF, and we had about 1.2 PF there, I remember. So we are making the capacitance 3 times larger. So the first stage has to drive 3 times more current into the parallel connection of this capacitor and the second stage. This would already increase the contribution to the distortion of the first stage. And then we are reducing the loop gain at low frequencies. So this doesn't sound very promising if we are considering the interaction between compensation of the amplifier and distortion, as with all the other techniques except with the phantom zeros. So still, being at this point, I can still state that the phantom zero compensation, and in the specific case of our amplifier at the input, is the best technique that we have seen so far. But this course is not about solutions. This course is about design considerations and techniques that you have, because sometimes a phantom zero is simply not possible, and then you need to do something else, and you need to rank your techniques. What is then the next one, and what is the price I pay to do it in a different way? Now we have a possibility of getting the poles in the right position. You see, I here changed them, made this capacitor large enough, and you see the plus sign is the end of the root locus. So then at 5.4 PF, I have 45 degrees, but with a bandwidth of Well, let's estimate something like 400 megahertz. While I started initially without compensation at 1.4 gigahertz. So only 30% of the bandwidth is left. Now, if you don't care about this, you can simply do it like that. But this was also, this is for this reason called bandwidth reduction. We simply changed the pole and we didn't put a zero on the pole. We just take one of the two poles and bring it closer to the origin so that we have a flat frequency response. So you see, this is the price you pay. Maybe we can also look at the circuit that we have, which is again the index file, and then it will automatically do the. So here you see the result again, a little bit larger. And of course, you can also plot the Bode plots after complete compensation and see that they are quite flat and that your bandwidth is reduced.